This is our last unit in the study of similar polygons. We're going to look at some properties of similar triangles, some special cases, special things that might occur. This first one, Theorem 7.4, is commonly called the side splitter theorem. And for those of you that will be taking the ACT exam this spring or next fall, maybe even in the summer, problems like this do show up on the ACT exam. So the theorem says if there is a line parallel to one side of a triangle, okay, and while we're going through this theorem, take a look at the picture in example 1. So a line parallel, we're talking about the line from I to E, and it intersects the other two sides, then it divides the sides proportionally. So IE is parallel to the base, VO, and theorem says that it divides the side from V to D and the side from E to O proportionally. What you might also notice is that it does cause two nested triangles. We have a small triangle on the top, triangle DIE, inside of the larger one, triangle DVO. And because that occurs, we also have corresponding parts of similar triangles are going to be similar. So we could set up the proportion from a small triangle to a large triangle, which we have done. There is a corollary that I didn't write separately, and it says if there are three parallel lines intersect two transversals. So three parallel lines intersected by two transversals, they can go any way, then the intercepted parts are proportional. So we're talking about these parts in here are proportional. And we'll run into some problems like that later. But for right now, let's just concentrate on the triangle. Have several examples here just to make sure that we understand how it's put together, and then we're going to solve some problems with this. All right, so first off, if we look at example 1, it says complete the proportions for the figure. And so we're going to identify the parts. Remember that the arrows, this little arrow right here, whoops, it's not drawing. Let me try it again. There we go. The arrowheads do mean that those sides are parallel. So keep that in mind as we work through the problem. So we have line IE is parallel to VO. It does intersect the two sides of the triangle, which means that it is cut those sides proportionally. So let's look at the parts. ID is on the left, and it's the short piece, and it relates to IV, which is the other shorter piece. What we're going to do is we're going to identify matching parts. ID is in a side of the upper triangle. IV is this lower part, so it corresponds to EO. This side splitter theorem gives us lots of options on solving for missing pieces. All right, let's try another one. Let's look at what we have and identify what's missing. We have ID compared to DV, so a small piece compared to a large, and you could also think of this as small triangle compared to left side of the large triangle, is equal to DE over, well, the large triangle is DO. Just matching corresponding parts. Notice on each of these, I wrote us some little notes. In the numerator, we put the top section. In the bottom part, I put the bottom section on the first one. And then in the second one, it was small triangle to large triangle. Remember, you can have the reciprocal of both of those. Whatever pattern you set up, you just continue in both fractions, set them equal, and you have your proportion that you can solve. Okay, let's try another one. Example 2, and I'll leave the first one where you can see it. All right, so this is the corollary, if you would. We have three parallel lines running through the middle. Remember, the arrowheads tell you that they're parallel. And our two transversals are the sides of the triangle. So you could think of PY as a transversal and YS as a transversal. So again, you can have more than just two parallel lines. It still cuts all these sides proportionally. So let's see what we have. And I've written 4 of them so we can match all the parts. So AY is the left side of the smallest triangle, and we're comparing it to LA, another small piece. So AY and YE are corresponding. That means LA, a short piece, must correspond to ER. You can say ER or RE, means the same thing. All right, let's try another one. And you notice I'm drawing on the picture. It helps a lot. So find LY. That's a long piece on the left. And we're comparing it to PL, short piece on the left. I have RS already drawn in, so short piece on the right. I'll give you a minute to see if you can figure out what should go in that top. And hopefully you said R to Y or Y to R, either way. Now I'm completing the fraction on the left and then doing the fraction on the right. It doesn't really matter what order you do the pieces. Let's change it up a little bit on this next one. PA, all right, PA is right here. And I'm going to go over and look at SE instead this time. Instead of going top to bottom, I'm going to go left to right. SE, all right, if we notice, they are the bottom pieces of that large triangle. Now we're going to compare it to AY, which is a top piece of the triangle. Well, if we match up the two sides, we must be going with EY. Lots of freedom here. Okay, the last one I'm changing up a little bit. All these others that we've been doing, we're using the sides, the left and the right sides of the triangle. Because we had a comment in here, right here, it says that we're causing nested triangles to occur. So we could have the proportion small triangle to large triangle. Instead of just splitting the sides, I want you to also notice what happens in this last example. I'm going to take AY on the left, and I'm comparing it to PY. All right, so it looks like I have small triangle and large triangle, 2 pieces. Now look at where we're comparing it to. AE is the bottom side of the small triangle again. So what I'm wanting for this last position, I need a bottom side. We're looking for corresponding parts. So bottom side of the large triangle. So we're looking for PS. It's kind of like fitting the pieces of a puzzle together. You match what's there and then look for what's missing. All right, now that we've matched up a few, let's actually use these to solve some problems. Got a couple of examples here. With each one, you're going to look at a picture, and there is more than one possibility for the proportions that you could write. You just write the one that occurs to you. I like to use small pieces rather than entire sides when I possibly can. Smaller numbers will allow me to do a little less reducing. All right, so first of all, identify what you're missing. I'm missing that piece right there. And that is a short piece from the right-hand side, and if I match it up with the left-hand side, it matches up with the 24. Now I can either put it underneath or in the same position in the same fraction. I think this is how we've been writing most of them, so let's just write it like this. Now I'm looking for other pieces that we have numbers for, and if you notice, I've got a 40 and a 32. The 40 is on, it's the top part of the right-hand side, so I'm going to put it under the x, and its corresponding part, the 32, is going under the 24. Notice 24 and 32 are both from the left-hand side. The x and the 40 are corresponding positions from the right-hand side. And then we solve it. Do remember that you can reduce fractions. 24 over 32, 8 divides into both of those, so we can reduce out the 8. It gives us much lower numbers to work with. So 4x is 120 using cross multiplication. Divide both sides by 4, and we do get x equals 30. And we were asked to find x. That is also the length from D to G. Never hurts to make sure things make sense. Notice the 32 is larger than the 24, so the 40 should be larger than the length from D to G, and it is. 40 is larger than 30. So the answer that we got made sense. Let's try another one. Find your x. All right, this time I'm going to write my proportion similar manner, just a different order. X is what I'm looking for, and I have another side on that triangle. So I'm going to compare those. X is to 10. X and the 5 are in corresponding positions. 5 is just on the top, and the 10 and the 8 are in corresponding positions. So I have x over 10 equals 5 over 8. Cross multiply, 8x equals 50. Divide both sides by 8. So that's 50 over 8. If we divide both of those numbers by 2, we get 25/4. And there's our answer. That is 6 1/4, by the way, for those of you who can't stand improper fractions. Make sure it makes sense. 5 is less than 8. 6 1/4 is less than 10. Looks like we have the right answer. And we could plug it back into our proportion and double check it if we prefer. Both of those were set up pretty much the same way. The order I wrote things down varied a little bit, but it still gave us the same idea. All right, one more. Here we go. Find your x. All right, I want the bottom piece, but here, this one's going to be a little different. I have the 5, a small piece, and this time I have the 8. So this is left, left side, and this is bottom of our small triangle. Everything here is small triangle. Equals. Well, we're going to have a little difference here. This 20 is the bottom of the large triangle. It's not just a part. It's the bottom of the entire large triangle. So on the top, we're going to have the left-hand side of the large triangle. Well, the left-hand side of the large triangle is an x. The left-hand side is the whole thing, x plus 5. Because we're using, instead of just pieces, like small piece and large piece of the two sides of a triangle in our previous equation or previous example, we're using an entire side of a triangle, so the bottom. So we have to make sure that we use an entire side when we compare it. All right, let's do some cross multiplying. 5 times 20 is 100. We're multiplying the 8 times the entire group. So distribute that. Subtract the 40 from both sides of the equation. And then divide both sides of this equation by 8. Need to do a little reducing. I could divide 4 into both of those. If you didn't catch the 4, you can divide out 2 times, and you'll still get down to the same answer. This is 15 halves is x, or for those of you who'd rather see a mixed numeral, that would be a 7.5, which does make sense. If x is 7.5, then that entire side is 12.5. Needs to be bigger than the 5, it is, and the 12.5 and the 20 makes sense for the sides of that large triangle. Several different uses. Several different uses. Okay, I'm going to stop right there for part 1. There is another theorem and definition we're going to look at, but I think we'll do this in 2 short videos rather than one long one.